Hello everyone. Thank you for attending the session, the energy session, for the audience in the room and for the audience online. My name is Ira Scheffer from Renewables Grid Initiative. This is a unique collaboration of European transmission system operators and environmental and climate NGOs promoting sustainable grid development across Europe. To me, co-moderating this session today is Frances Roa from Barcelona Supercomputing Center. And today, we have a packed agenda. We will have elevator pitch of the energy research under Destination Earth. We also have a panel discussion, panel expert discussion, and then we have some time for Q&A towards the end of the session. Now, during this session, we will discuss Destination Earth energy research and its applications from the perspective of key users. This means policymaking, energy developers, energy system planners. For joining the discussion already now, please, you can scan the QR code here and suggest comment or ask questions throughout the session, and we'll try to address most of them later on in the session. Now, we hope that within the next hour or so, you would have a better understanding of what energy research under DestinE is and how it can be further developed considering climate change, extreme weather events, and what are the required steps or the needs to address their impacts. Now for that, we will address some of the issues related to extreme weather events, to dynamic line rating, to machine learning demonstrator, and also for enhancing forecasting in extreme weather events. So for that, I'm happy to present four researchers that lead Destination Earth energy contracts. They will be pitching their projects one after the other, providing us a glimpse of the project's goals and relevance for users. Sorry. Okay, they are Peter Monia, the head of the Scientific Service for Meteorological and Climatological Research at the Royal Meteorological Institute of Belgium and a professor at Ghent University. My colleague, Frances Roa, an atmospheric scientist working on climate services and computational workflows for the wind energy sector at the Barcelona Supercomputing Center. Irina Schicker, a meteorologist and a senior scientist at the Austria's Geosphere, focusing on machine learning and statistics for weather and renewable energy forecasting. She also leads several projects on the topic under Destination Earth. And Bruno Schiska, a scientist at the German Aerospace Center, leading energy research under Destination Earth, and also a lecturer on energy meteorology at Karl von Ossietzky University in Oldenburg. So we will hear now a very short elevator pitch for these four presenters, and then we move on. They will set the scene for the panel discussion that will follow. So first, please, Peter Monia.
Okay, so thanks, Ira. Maybe just as a start, so the title here is dynamic. It's about dynamic line rating. So there's not so much all the ones who are brave to stay and listen. Just if you know what dynamic line rating is, I don't know if you know it, but maybe if you know it, just raise your hand. The people here are not allowed. So it's about 20%, I guess. So my pitches will be to explain what dynamic line rating is, and then I very briefly say what we plan in this project. Does this move forward? Or can this go to the next slide, please? Up. No. This one. Okay. Okay, so dynamic line rating, it's about transmission of energy through power lines. And we know that this depends very heavily on weather conditions. And of course, Destination Earth is about, let's say, modeling extreme events and weather using the DTs, the climate DTs and the extremes DTs. But this project is about the extremes DT. It's basically about weather forecasting. And so there are basically two approaches. This is summarized on this slide here. There is a sort of light one and a more heavy one, a more ambitious one. So as you will see on this next slide, this work was done in very close collaboration with end users. And we are discovering this because we are meteorologists. We are not experts on transmission itself. But the points of view vary a little bit on this. And let's say with the first end user, they prefer to have some sorry, this is not the one. The first users prefer to have something like this. And basically, transmission system operators have to sometimes take heavy decisions. They have to intervene in the grid, and they can have a very big impact, like outages or cutting some of the providers in the system. So if they make decisions, they have to be very sure. And sometimes easy or simple is more useful than complicated, because then the people who have to decide are sure that they understand what they have to decide about. So one of the users basically prefers something like this, and this is a map that we produce for Europe, where it indicates conditions. So you read here very favorable or critical, and somehow we can compute on the model what it will be. And that's already useful. And that's something that we are now implementing within Destination Earth, the DSP, and so on. Now, on the other side here, it's written here, may have the ambition, this is a more complicated exercise, to have a continent-wide screening and identifying single critical spans. And I invite you to look here. This is a picture from Austria, and here, this line, if you can see it, it's a power line, and the segments are something like 500 meters. And usually it's maybe, oops, no, this is, so sometimes one of these 500 meters is critical, and we have to spot where it is, because that can be the one that blocks the system. So the challenge that we took is to use the 500 to 750 extremes DT and see if it can add some value, basically, in forecasting these kind of events. But you see, it's important because a study that was done in our community actually showed that the variation of the capacity to transport energy varies between minus 40% roughly and plus 150%. So if you take basic decisions, it's okay, but there's a lot of capacity also to optimize your decisions. And then we would like to go actually to the 500 meter to give more information. But I can tell you this is a challenge, and for this we need to interact with stakeholders. So I first show you this. Currently we are discussing with these entities here, so there are 5 countries involved. There's basically the TSOs here at one side, and we try to understand more and more what they want, because we will need to do some tailoring to satisfy their needs. And the other thing that we are doing is we are implementing this in a kind of an interface that will be put on the DSP in some future. We are almost ready, but it's not quite complete. So that's where we are currently, and that's basically my pitch that I wanted to show to the public.
Thank you very much, Francis.
Thank you. I want to do a small exercise with you. So you should imagine yourself having a wind power plant, yeah? And then you imagine that you live in a world in which the climate is changing. Yeah, you got it? Then you imagine that to assess what's going to happen in the future, we are using data from the past. Yeah, you imagine also that? So imagine now that you are not imagining, and it's actually what's happening. So the sector is using data from the past to assess what's going to happen in the future. So with the energy use case from the Barcelona Supercomputing Center in the Climate Adaptation Digital Twin, we want to help the sector to overcome this. How do we do that? So I will have with a small video that we'll start showing now. So we get the high-resolution simulations that together with them, we run the variables, we get the variables that our key users need for the assessment, for the pipelines, such as production indicators, such as capacity factors for different wind turbines, or extreme events, like low and high wind events. But not only these ones, but with co-production co-development approach, we can get tailored indicators that are useful for our users. For example, this one was our key user, Ocean Winds in the North Sea. They asked for wind distributions. So we said, okay, let's find out how can we get them from you. And this is something that we got operational into digital twin. And more to come from the interaction with users. So happy to talk to you if you want to get some indicators into the climate DT. Thanks.
Okay, so we're moving away from the climate to the more local scale and the sub-kilometer scale. And no? Is it moving? No. Yeah. So the renewable energy impact sector model in the on-demand extremes twin has 4 components. It has the renewable tailored detection algorithm to detect extreme events like ramping for wind and solar power production. It has the tailored numerical weather prediction models that do account if you have a wind farm in your domain or more wind farms, and know where every wind turbine is standing, what's the hub height, what's the rotor diameter, and can include this into the forecast and see wake effects of the wind turbines on the downstream turbines. So we can simulate this and use this high-resolution forecast model to post-process wind and solar power for on-farm level, on-turbine level, if we have the information, or aggregated for a country or municipality or onshore, offshore regions. And for the post-processing part, for the solar, we have a separate component, the nowcasting component, where we can rerun the post-processing on the day of a thunderstorm event, for instance, add information from the nowcast to our forecast for the power plant, and include the information when the ramping will be happening. And one of the new parts that we are going to focus on in phase 3 is the co-design what-if events. We will look into what would happen if this event, like Storm Boris, would have a different setup of wind farms and layouts, or you have new technologies already installed or future technologies, and we also look into future events from the climate DT, like future heavy storm events, and play around a bit with the different turbine setups, turbine types, and see what would happen if we had different kind of setup there. So these are the 4 components, and have some results if you're interested, but I'm happy to discuss this a bit more in today or tomorrow, whenever you see me. And thank you.
Okay, good afternoon. Just another energy topic. So what we are dealing with is what is called resource adequacy assessments. What you do is you model and analyze the balance between energy supply and demand to basically derive decisions to ensure the security of supply for future conditions, right? And what you usually do for this one, you combine weather data. In most cases it will be Copernicus or destination Earth data, and take energy systems data as well, so some databases for installed capacities for transmission, generation of electricity, and then you run simulations with this one. My visualizations look like this one, so I don't have a visualization team as BSC to do fancy simulations, but visualizations. These simulations are usually optimization problems, which can become quite complex and then time-consuming and also memory-consuming. So what we try to do in this machine learning demonstrator is basically to get rid of these nasty simulations and replace this with a machine learning approach. So what we do is we apply what we call physics-informed neural network to build a surrogate of the energy system. This is driven by, as I said, Copernicus data, but also by of data from the climate TT. And yeah, why is this important? So first of all, this approach has been proven or has been found to get better results than compared to just purely data-driven models, because here we have some information about the power system implicitly taken into account by this neural network setup. And of course, if we have a speed-up gain, we can simulate a large number of scenarios, right, to better picture uncertainties and then support decision-making for the electricity system. Thanks.
Thank you for all the speakers for giving this introduction to the different contexts in energy in Destination Earth. And I think this is a great introduction to how do the we want to see how our panelists do see this context and how can them interact with this work that is happening. So it's my pleasure to present the panelists. First, Andreas Zucker. He is a policy officer at the chief economist. He is policy officer at the chief economist unit in DestinE, the European Commission, and he has rich experience in energy policy, including the EU Joint Research Center. Then, in the left, we have Gabriela Basarab. She is a communications and policy officer at Current, contributing to the organization work and on advancing innovative grid technologies for Europe's energy transition. And she collaborated with the European Commission DestinE. Then, in the center, we have Miguel Cordova. He's a director of MetOcean and energy assessment at Ocean Winds, with professional experience in this field for over 20 years. And he has academic background in physics and data assessment. And last but not least, we have Laurent Debout. He's an expert and lead scientist in weather and climate with the French transmission system operator RTE, working on long-term planning in ENSOE, and he's also founder and contributing director of the World Energy and Meteorology Council. So we have heard these 4 presentations, and we would like to hear from you your opinion on some of them. So I would start a question to Andrea Zucca that is, compared to the existing scenario building approaches and tools, what aspects of destination output do you find more beneficial for the GNR? For instance, what could be the added value of the what-if scenarios, such as those explored in the Extreme City presentation from Irene?
Okay, thank you very much, and thanks for these excellent pitches. To give you a little bit of to take one step down, you're asking what could be of interest for policymakers, because this is what we are at the European Commission. And so for policymakers in the Directorate General of Energy would be the same as policymakers in member state ministries for energy or ministries for the economy. What do we actually do? Well, we have to design and implement long-term policies. Long-term and short-term, but very often long-term policies, and we all know that the European Union is committed to transitioning to a net zero economy by 2050. And in addition to that, we have a number of intermediate goals that we have set already for the 2030 time period. Everyone can might follow, many of you might follow the discussions around. And we are now busy with designing the policies for the decade 2030 to 2040. What does that mean in terms of energy? It means that we will definitely have we need to design policies for a world which is technically changing from always changing, but definitely in our transition to a low carbon and zero carbon eventually economy, we will see new technologies. Long story short, a lot of renewable energy, and renewable energy is to play a role, not only but it cannot be underestimated, and that poses a number of questions, and many of the questions have been addressed today in this workshop. Many are related to weather, and this has basically three implications. One is long-term planning. What do we actually need? Because understanding extreme events is important, because extreme events can define the design of the entire system, and that has an implication for the cost of the system. It also has an implication on the markets, because energy is traded on markets since our deregulations at the beginning of the 2000s. Therefore, we need to understand how extreme events, but also how dynamic line rating, what the impact could be on prices. And this is important because important assets that could play a role, or that will play a role in the future energy system, like anything providing flexibility, is dependent on the revenues to be captured on markets. Therefore, understanding this dynamic is of crucial importance. And finally, the technology required for operating such a system will depend on the details of the system, and the system that we will have in 10 years will very likely mean investments in certain new or emerging technologies. So those colleagues busy with technology policy need to understand where to put the money for technology development, and therefore, again, anything related to the operation of the system, whether it be extreme events, whether it's going to be how the network operates because of, let's say, dynamic line rating, whether it is how to, having the possibility to very rapidly generate a picture for the system dispatch will help us understand how new components could fit into the whole system. So from a bird's eye view, everything that is done here is crucial for us. It might not materialize into all our methods immediately, because we're using a toolkit of different methodologies, some of which are very conservative, but nevertheless, it immediately plays a role in being able to understand the system is essential for us. I hope I could answer your question a little bit.
Yeah, thank you very much. Then the next question goes to Laurent. I see that you already got the mic. So the question goes, what would be the added value of integrating the machine learning based climate information that we saw from the speech from Bruno in the work done by RIT or ENSOE in energy system planning, and what could be the challenges in integrating these machine learning approaches?
Yeah, first of all, I must say that I was very impressed by all the presentations over the last 2 days. It's really impressive to see what DestinE has achieved with so many applications, so many models, and so on. It's really, really impressive. And that's also the case for the 4 prototypes we've been presented, and so including the machine learning one. But I fully agree with Andreas that all of them are very interesting for the energy sector, and it's really promising of what we can do with all this once the link with users is maybe more pronounced, more developed than it is currently. But I guess it will come in the coming months, and that's very interesting. To come on this machine learning application, so maybe just to make a step backward as well. So as TSOs, so we have to ensure the balance between supply and demand at every time step, which means in operational conditions and real-time conditions. But also we have to do prospective studies on how the power system will work into the future for the next season, for the next 10 years, or even for the next decades, up to the horizon of the energy transition to 2050. And so for that, we have to run power system models. That's currently what we do. Those models are based on physics, basically, so physical equations, electronic and electricity physics equations. And this new approach based on machine learning seems very promising because those physical models are basically solving optimization problems, which are extremely complex with hundreds of thousands of variables, millions of constraints, and so they are very slow to run. And so having machine learning methods which are very, very quick, especially in their inference time, is very interesting. So we are following what Gerard and their colleagues are doing at the moment. It's very, very interesting. But of course, there are some questions which come with that. Maybe the first one is what is the actual gain in computation time, which is one of the issues, one of the bottlenecks at the moment. And the second one would be about the explainability of the models. Are we sure that the model provide the good outputs for the good reasons, as for any AI model? And maybe a more important one is the capacity of those models to extrapolate in the future, because they are based on machine learning models, so training on actual data, observations. But what about their capacity to model and to provide outputs in a power system that will be different in the next 30 years, for instance, if there is much more wind energy or solar energy and so on? What is the adaptation capacity of those models to provide insightful results into the future? But yeah, the results seems very promising. And a question I would, in addition to the first one I asked, maybe to Bruno, would be what would you expect from TSOs and from NSOE as well to help you develop further those models and hopefully to have a mutual gain in the future for having better models, faster to run, which will allow to explore a much larger panel of possibilities, of scenarios for the future than we can do currently with limited time resource and CPU resource and so on.
Yeah. Thank you very much. For sure, the machine learning is here. For sure, machine learning is here to stay, and a challenge to get it into the decision. Then thanks for your answer. Now I would like to move to Gabriela. So current published recently an assessment pointing on identifying and implementing dynamic line rating, that DLR, across European grid operators. And how could these approaches or tools generated from Destination Earth, such those explored in RMI, address this challenge that you published?
Thank you for the question, and also thank you to the panelists and all the amazing work that has been done. So as the other panelists already have mentioned, I think the potential is there to influence long-term planning and long-term operation of the power system, so I'm not going to go into that again. So looking more into what can be achieved now, or more into a near-term time frame. Currently, our energy needs are so great and the grid cannot cope with it. So apart from looking at grid expansion, which is very important, Current's mission is also to get most out of the existing grid. And this is where grid enhancing technologies or innovative grid technologies come in, such an example being dynamic line rating. So for us, dynamic line rating is already a mature solution. We already know the benefits. It already has been demonstrated globally. China, for example, has the entire power system using DLR. In the US, it's already being deployed at scale, and Europe is a bit behind in this. So we're very glad to see that we were very glad to see the use case on DLR again to showcase the benefits. When it comes to deployment, however, what we're seeing, it's very hard to see what is being deployed currently and what it is being used in operation based on open data. So this is the study that you were talking about. We did a DLR adoption map, and what we saw is that Belgium and Germany seems to fare a bit better compared to other countries, but a lot of data is missing. And why is that? So from our members, what we're hearing, and also from different roundtables, is that the incentives are not necessarily there, because currently we're focused on very CapEx heavy investments, and system operators might not be incentivized to deploy more digital solutions. It's also adding a lot of complexity to the way that they're operating the grid. So nobody's blaming them. We're just trying to move forward and unlock capacity in the grid. It's also that TSOs are facing a lot of challenges themselves. There's a lot of priorities on their list. There's a lot of projects they have to do. And what we often hear is that they're lacking the skilled labor force to actually implement such innovative solutions as DLR. And let's not forget that system operators have very different sizes and very different resources. So here is where the benefit of such an open data data set on DLR could be useful for, is for EU-wide deployment and EU-wide observability. Because if this is where the real benefits could be unlocked. If you only deploy DLR in isolation on a specific line, you cannot really capture all the benefits. And that's why we really appreciate the work that has been done, and we see it as being deployed as a baseline solution, offering system operators at different levels, DSOs at local level, maybe that don't have the resources, an overview of where they can build out, where they can implement DLR, where they can implement other innovative solutions. And let's also say that DLR should not be seen in isolation. We should really focus on how to deploy all these technologies together. So thank you very much.
Thanks, Gabriela. Yeah, for sure. Improving the DLR in Europe, it's a challenge. Let's see what we can do. Now I will give the floor to Ira to ask the last question to the last panelist.
Thanks, Frances. I'm very happy to have the chance to ask the last questions to the panelists. Miguel, this is one for you. What parts of the co-design process have been beneficial to you as a key users of DestinE tools or outputs? And how has it allowed or will allow to improve your project planning? And equally important, what are the challenges in this process?
Yeah, so I have to say that being, in cooperation with Frances and with all the BSc on the co-design is a really good journey, because I personally feel that from all the previous climate models, we have been just seeing the people dancing, and now, thanks to Frances and the team, we have invited to the dance floor, so this is very good. And what I mean by that is that for us, we do have more pipelines or workflows, and we see some variables that are critical for us, but not all of them are easily accessible on the climate models, on the current climate models. So by inviting us to provide our feedback and our suggestions has been very useful. For example, the capacity factor in our one of the wind farms, besides the aesthetic, which is pretty cool and it helps quite a lot for us, it is important to know, because as Frances was talking earlier, our current base case is that the climate, in terms of the wind, it is a very slow motion thing changing. So we need to know at the end of the day if this is true or if it's false. because currently this trend, if it exists, is masqueraded by the internal variability of the wind, and it will be very useful to have a clue about what is going to happen in the future. And besides kind of like the wind itself, again, you know, as many other people have been talking about extremes, we are very keen on extremes because we do design the platforms, monopiles, jackets, wind farms to resist, you know, big waves, big winds, all together at the same time. And again, we look at the past, we make our, you know, extreme value analysis, these Campbell things and complex stuff, but we need to have the climate model there also giving the feedback to know that if these assumptions are just way off, they were perhaps, you know, way too pessimistic, so we are over-designing things or not, because this is also a matter. We want to reduce the capex to make energy, you know, cheaper for everyone, and this goes with hand with a better information for the future. And what else? How we use this data? Yeah, as I said, we need to give to our teams, you know, all this information. And with regards to the challenge, the main challenge that I see is the verification of the models. You know, we are, you know, very happy to use this information, but first of all, we need to, you know, realize if it's good or not, because at the end of the day, you know, wind farms, as many other industrial things, are really costly and, you know, are really, really expensive. So every single variation of the estimate is plenty of money. So before just throwing conclusions, we need to have a sense of uncertainty. And last, the challenge, the other challenge, is how we use this data. So just assuming that it is pretty good, you know, we will need to incorporate all this data into our pipelines, into our workflows, which are very in-house. And after these 2 days here, I think it's going to be very easy, because there are plenty of people doing impressive things. So this is kind of like it's not become a challenge anymore, I guess. It was a challenge, you know, for me before coming here to Brussels, but I think it's going to disappear. The verification challenge will be still there, but not the other one. And that's it. Yeah.
Okay, thank you very much. So thanks for all the panelists and the speakers. Also, thank you very much for that. I think we have a little bit of better understanding about the... no, you don't see it now. Can you please switch to the... thanks. Okay. We have a little bit of better understanding of from the user's perspective, how they see Destination Earth, the energy research under Destination Earth, about some of their expectations, what they need to overcome, and how to get these links together between the outputs of Destination Earth and the user's needs, how they will apply them eventually. Now we want to move to questions, a Q&A from the audience, but also online. Please, if if you're a bit too shy to raise hand or ask questions here, also you can send questions via the Slido. Please click here for the QR code. So I will approach the audience first. If there is any questions for the panelists or for the speakers, the presentation that we heard before, please raise your hand and we'll approach you with a microphone. And please don't be shy. I know it's close to 3 o'clock. Break is on the way, but okay, a bit too shy. So let's move for the questions from the from online participants or from the Slido. We have a first question. I'm not sure if it's addressed for the panelists or for the speakers, but is there a distinction between onshore and offshore wind capacity factors? And are capacity factors also for PV available?
I think I think this is for the energy use case from the BSc. First, thanks for the question. We have several turbines being input for the computation of these capacity factors. So indeed, we have different capacity factors for different wind turbines. So normally the wind turbine, of course, on sea will be different from the ones onshore. And we do provide the different capacity factors for the different wind turbines. And regarding the PV capacity factor, we have indeed also PV potential there in operation. We are expanding the solar part of the energy use case, and it's something that was not brought in here, but it's indeed also important to have the solar part integrated into the decision taking as well as the wind. Yeah.
Maybe I could make a compliment on that because and also make a link between DestinE Earth and Copernicus because at ENSOE level, so we have an expert team dedicated to climate and energy datasets that I'm leading together with Aaron Zucker, who's in the room. And over the last 3 years, we worked with the Copernicus Climate Change Service to develop the so-called Pan-European Climate Database in its version number 4. And this database contains both climate data, so mainly temperature, precipitation, solar radiation, and wind speed, both for the past, based on ERA 5, and for the projections from 6 semi-physics models and 4 SSPs. And so from that, we have the climate variables, and we have also energy information for 10 different onshore wind technologies and 3 offshore technologies, as well as 4 typologies of PV panels, so rooftop residential, rooftop commercial, and so on and so forth. But it's based on semi-physics models, so rather low resolution data. And what we would like to see and to encourage in the future is, of course, taking advantage of what has been developed in DestinE Earth with high-resolution climate digital twin, because for sure, for PV applications and wind applications, having higher resolution, geographical resolution, is very important as it helps to capture very local features that are not present in the semi-physics models. So there's probably a way for collaboration between both programs there. And we clearly hope that this would be something that will be investigated in the future. By the way, there is a new C4S contract dedicated to the energy applications starting later this month, in principle. And one of the tasks that will be addressed in this project is to assess whether and how we can incorporate the climate DT simulations into that process. Having in mind that this dataset, the PECD, is going to be used not only by ENSOE for the next European Resource Adequacy Assessment study, for instance, but also by national TSOs, starting with RTE and TENET and many others. So there's clearly a link to be made here between both programs, Copernicus and DestinE Earth, which should not be too difficult because both are implemented by ECMWF and the partners we all know very well. So really, I think there's a very nice avenue here for the climate DT simulations for the energy sector.
Thank you very much, Laurent. Thank you very much, Francesc. We have 2 more questions from the audience online. One is the service for replacing turbine layouts for specific weather events available on the DestinE platform. Also, perhaps it would be useful if the people asking the questions, if they want to direct the question to the panel or the speaker or specific panelist or specific speaker, please do so.
Yeah, I don't know on the second one, I don't know if you have anything to say. It seems related to what we do.
Yeah, Irene, if you want to bring it back.
Yeah, I think that was for the what if scenario case, the questions. And the service is not online yet, but it's on the DestinE North GitHub repository, in case the person who asked is allowed to look into that, or I can point person to that, or we discuss it, but it's not yet there.
Okay, thank you. Now it's a question for DG Energy, for Andreas and Laurent. How much are future climate projections used in current energy grid planning? Andreas, do you want to start?
Well, I will hand over this one to Laurent, because the role of the European Commission in the, you're probably referring to the planning process of the, so basically to the three-step process of creating ENTSO-E, TYNDP scenarios, running the needs assessment, and the evaluation that leads to the list of project of common interest and project of mutual interest. And the role of the European Commission there is actually to ensure that the process is done correctly. I could give a technical answer, but I refrain from it and I leave that to Laurent.
Thanks, Andreas. Yeah, like I was saying a few minutes ago, so we, over the last 3 years, we developed this new pan-European climate database, which is exactly designed for such purposes. So before that version of the PCD, we had one which was based only on reanalysis data, so it was based on ERA 5. But for sure, when you want to make prospective studies for the next 10 years or even 30 years, looking at past climate data is not relevant anymore, especially for temperature, because there's a clear trend, and looking at what the consumption of electricity will be in 10 years or 20 years based on 1990 to 2020 data is not relevant at all. So that's why there was this endeavor 3-4 years ago, in which we designed this work with Copernicus, and we now have these simulations available. And so again, now we have a strong database. It's only 6 climate models, but it's better than nothing. And we also have 4 SSP scenarios. So we have the 2.6, 4.5, 7.0, and 8.5. So we have a large choice in terms of energy scenarios that we can take into consideration in our studies. So both at EU level for ENTSO-E, but also at national level for RTE. And I can mention that on our side in France, so at the moment we are doing a huge study to update our Energy Pathways 2050 study that was published 5 years ago. So we are looking at what the French power system inside the European power system might look like in 2050, considering different scenarios, so climate scenarios of course, but also scenarios for the development of the economy, the development of technologies, the development of behaviors of consumers, and so on and so forth. And so we are basing this study on the PCD, which allows to take into account this large variety and diversity of climate models on the one end, and energy scenarios or climate scenarios on the other end.
Thanks a lot for that. There's another question, and I think it's directed to the private sector people here, perhaps or for the industry people, Laurent and Miguel. To what extent do companies currently incorporate climate projections into their decision-making processes? For example, how much weight is or would be given to projections for 2040 or 2050 in the design, financing, and operation of the infrastructure assets?
Me again. Okay. So yeah, basically, I think I already understood, responded to the question just by what I said. But what I can add is that in addition to the kind of studies we do for how the system will operate how the power system will operate in the future, considering assumptions based on behavioral changes, economic changes, consumption increase, and so on and so forth. So we also take into consideration climate scenarios for the sizing and the dimensioning of the system. So here we are talking more about the resilience of the power system to climate change, both for upgrading or improving the existing assets to make sure that they will be able to operate under change conditions, but also to dimension, to size the new assets that will be built in the next decade. As you may know, the French power system is going to be restructured a lot because many assets are more than 70 years old, built just after World War II. So we need to increase the resilience of those assets. And so, as for instance, overhead lines have a life cycle of around 80 to 100 years, which means that the ones that we are building now will still be there at the start of the next century. Of course, we need to make sure that they will be able to operate under a changed climate. And so for that, we need to take climate change into consideration and at least to make sure that this adaptation plan is relevant with what the government has decided, which is known as the reference trajectory for the adaptation to climate change, TRAC in French, which more or less targets a global increase of 3 degrees in temperature by the end of the century at the global level, which means 4 degrees for France. It does not mean that we stick to this value, because of course we try to take into account uncertainties. And when it comes to dimensioning very expensive assets, we also need to take into account the most pessimistic scenarios, for instance 7.0 or 8.5.
Yeah, perhaps on the sorry, for a wind energy company as Ocean Winds, we are not yet there. We are not using at all these projections because the wind and the waves are very complex variables, and the current climate models are not providing sufficient data quality for this. And this is actually one of the key points about DestinE Earth, to be able to provide high quality projection for these variables. Yeah.
Okay, thank you very much. Now we come to the final few minutes of the session. So before we conclude and do the official thanks you, we actually want to know a bit more about you, the audience, the participants in the room and online. We have a very short survey here up on the slides. Provide a little bit of the background, who you are, why are you here, and also a few questions related to what you heard today about the panel and the projects under Destination Earth. We'll be very happy to hear your input also. Take a couple of minutes. The survey will be open also after this session ends, a few minutes after, so please take the time to fill it in. And that I would like to hand over to Francis.
Yeah, move to the podium. Yeah, as final words to the audience and to our dear panelists and speakers, thank you very much for this insightful session. I think that we can get more, we got an overview of what is happening in the energy part in Destination Earth and how are the views of key partners. So thank you, the panelists, and thank you all the speakers and Kat for preparing the survey that you are answering. Thank you very much.